Greetings, chemists. This is lecture going to be about the difference between fission and fusion, which is really the difference between big atoms falling apart versus small atoms coming together. And I don't mean to suggest that small atoms can't fall apart and that big atoms can't come together, but we will see there is a difference in how they do that. So, I'm going to start with, let's go back to that band of stability. I remember from a previous video, we talked about the idea of the ratio between neutrons and protons in an atom, and that if you look at all of the atoms that we know of that are stable, you find this trend sort of like this, where it comes sort of like a straight line and it bends upward. As you get to heavier and heavier atoms, you need more and more neutrons to hold them together. So now let's talk about stability of these nuclei relative. Even these stable nuclei, some of them are more stable than others. And I'm going to point out a very specific nucleus, iron. Okay, iron has 26 protons and 56 neutrons. At least the most stable isotope of iron has 26 protons and 56 mass, not 56 neutrons. This is the most stable element, or I should say nucleus. We're not talking about electrons here. This is just the inner configuration of protons and neutrons. Nucleus. Period. On the periodic table, in the universe, so far, this is the most stable element. Now, if you are not, so let's talk about how that affects energies and things. So I'm going to define two terms. If you were to take, let's say, two protons and smash them together at high energy and they fuse into one nucleus. So these used to be two separate nuclei, and I smashed them together, and now this is one nucleus. This would be a fusion event. And if I were to take those two protons and smash them together with a neutron, and they formed two protons and one neutron, that's another fusion, and et cetera, et cetera, et cetera, et cetera, et cetera. So fusion is the process of taking two separate nuclei and putting them together. Usually it takes a lot of heat to do this, a lot of pressure, and forming a bigger single nucleus. Okay? The other term I'm going to give you is, let's take a big nucleus. Let's say we have 8 pieces in it. Let's make 4 of them protons and 4 of them neutrons, and let's say that nucleus splits, and that piece flies off that way, and this other piece flies off this other way, till we have 2 nuclei of 2 protons and 2 neutrons each. That splitting event we call, this is a fission event. So fission is a process by which one big nucleus splits into 2 smaller nuclei. It's the exact opposite of fusion, which is 2 smaller nuclei fusing together into one big nucleus, okay? Here is why iron, here's where we can relate these processes to iron. If you took 2 nuclei that are smaller than iron and fuse them together, they're like a fire. They give away energy, right? When you react oxygen atoms with like a wood log or something, when oxygen reacts with wood, it releases energy like a fire. As a fire, you could say. When you put 2 nuclei together that are smaller than iron and fuse them together, and they stick and become one nucleus, that gives away energy. It's like a fire. So fusion releases energy or produces energy. You could say, not creates, that's a bad word. Fusion releases energy if the nuclei are smaller than iron. The nuclei that are fusing together. Now imagine a separate situation. This is maybe harder to imagine, but imagine when you took the match and you tried to light a log on fire. You tried to react oxygen atoms with a log. And instead of producing heat like a flame, it sucked heat in like an ice cube, and it made it colder. You would never get, logs just wouldn't burn, right? Because every single time an oxygen reacted with one of their atoms, it would take away energy, and how would it keep going, right? Fires only work if they stay hot. We'll talk about that in the kinetics chapter. So what we find is that if you took nuclei that are larger than an iron nucleus, that are bigger than iron 56, okay, if you took nuclei bigger than iron and fuse them together, you can do it. You can physically make it happen. But it becomes like an ice cube. It sucks heat out. It drains energy. So fusion absorbs energy if the nuclei, I keep drawing two eyes in there, but I actually think it's only one. If the nuclei are larger than iron, than an iron nucleus, you could say. So you can take uranium and plutonium and fuse them together. That's physically possible, but it would be a very cold reaction. It would take away energy. It would not generate anything. Fission is the opposite. If you try to take a helium atom and split it apart, and by a fission event, that can happen. But when it happened, it would absorb an awful lot of energy. Whereas if you tried to fuse this helium atom and this if you took something much larger than iron, like a uranium atom, when a uranium atom splits apart, it gives away energy like a fire. So let's do that. Fission releases energy if the original atom, the nucleus, is larger than an iron nucleus, and the opposite, fission absorbs energy like an ice cube. Ice cubes absorb your heat, that's why they feel cold. Fission absorbs energy if the nucleus is smaller than iron. Okay, and so there are two sorts of standard ways to think about this, or practical ways to think about this. We have a reactor technology. So when we want to get electricity and get electricity to flow, what we usually do is we find a way to spin a magnet. So we take a fan blade, and if you take physics, you'll learn about this. We take a fan blade with a magnet inside of it. Let's put a little north-south magnet in there, and we want air to go across it and spin the magnet. So we boil water. We put a big tank of water right here with a tube going past the fan. We fill it with water, and then we light a fire underneath it, and that boiling water makes steam and it spins the magnet, and that's how we get electricity, okay? Now, you can burn all kinds of things. You can burn wood, you can burn coal, you can burn diesel fuel, whatever it takes to boil the water and spin the fan. So what clever scientists figured out was that uranium is like a fire, because uranium has a much heavier, it's, remember, uranium-92, 238, that's the mass of a uranium atom. And look at an iron atom. Iron is only 2656. So This is so big compared to iron. When this thing falls apart, which it does, it undergoes a fission event, it gives off lots and lots and lots of energy, just like a fire. So instead of burning all these chemicals that give off, really toxic fumes plus CO2 and things like that we don't want in our atmosphere, these scientists said, well, why don't we do this? Why don't we take a big rod, a big piece of metal made out of uranium, and another big rod, and another big rod, and we'll dunk them in the water, and when they're reacting, when they're doing their fission thing, they will boil the water into steam, and that's what's going to make my electricity. So this is called a fission reactor. Okay. Now we do this all the time. There's lots of fission reactors out there. By the same token, if we were to take a fusion reactor, for instance, if we were able to take two small nuclei, right, like two helium nuclei, let's say, and fuse them together and boil water with that, we could create electricity by fusing, but they would have to be smaller than iron to do it. Now, they're working on this. I say these being scientists largely in Southern Europe, but some other places as well, have made fusion reactions. They have taken small nuclei and slammed them together and create or generated energy. They have not yet figured a way to safely push them together and create enough energy and also at the same time spin a turbine. Okay, so that hasn't happened yet, but we're working on it. And that could be something, if you are interested in this sort of chemistry, they badly need more engineers to work on the problem. So fusion, let's go to that. The big place we see fusion happening is one of the problems with fusion right now in the fusion reactors I've seen. It's a big tube, and there's like a donut in the middle of it. And inside the donut, they have lasers, and they focus those lasers on the material, whatever the nuclei are that they want to react. They shoot them with lasers until they're moving really fast. They get these atoms moving real fast, and then when the atoms smash together, they fuse, okay? So they use a laser igniter to start the process, and then that creates the fusion reaction. Now, that's hard because you need really strong lasers with a lot of energy to get a lot of heat out of it. It takes like 1.5 million degrees, I think, to make fusion happen, and a lot of pressure. Well, there are places that naturally do that. For instance, the sun. So the sun is 1.5 million degrees in some layers, and so inside the sun, hydrogen, it's mostly hydrogen, mostly a bunch of protons. There are electrons as well, but a hydrogen nucleus is mostly single protons. And they're at such high temperatures and speeds that they will frequently crash together and form heavier stuff. So if you can get 4 hydrogens to smash together, they will also emit a couple beta particles. You can get a helium nucleus, for instance, and that would be a fusion reaction. And if the helium smashes together and forms, carbon and oxygen and things like that, you even get more heavier elements. Well, stars can keep building. They can keep smashing this stuff together, getting heavier stuff. There's maybe a helium. You can smash together and get a carbon. I could try and draw a carbon, but it's 12 of these. So there's a carbon, and I'll pretend half of those are protons. So, and you can keep building those up, and every time they smash together, they give off more heat, which keeps the sun very hot and produces and keeps the fusion reaction going. It's like the log burning. Every time one little piece of the log lights on fire or catches on fire with the oxygen, it reacts, it gives off more heat, which causes the next one to go. It's a cascading reaction until you get to iron. So at some point, you will have smashed together enough atoms that you have made an iron atom. So you get like some iron in the middle of the star. Well, fusion can still happen, right? Iron can smash together with helium or with hydrogen and make something higher than iron, right? You can go up to cobalt and nickel and zinc and things like that. The problem is, like I said before, when a nucleus larger than iron is created, it becomes cold, right? It's like an ice cube. So once you get iron in the core of the star, once enough fusion has happened to start creating a significant amount of iron, any more fusion reactions that happen will cool the star off and take the heat away and fill it with, I use the ice cube analogy. Imagine filling a fire with ice cubes, pouring ice cubes on fire. So once iron starts to accumulate in the star starts to get colder and it starts to die. It starts to grow dimmer. It starts to lose its energy. All right. So iron is the beginning of the death, I know, super morbid, of the star. Because it happens to cool the star off and take away its energy. Now, this is the qualitative side of fusion. There is math involved, and we'll do a little bit of it. So I'm going to introduce to you a style of chemical reaction equation. And I'm going to start with a sentence. And here's the sentence. Carbon 14 decays by emitting a beta particle and becoming nitrogen 14. And I think I've mentioned this in a previous video. That's a sentence. As a chemist, of course, we would like, chemists are lazy, and we would not like to have to write out a sentence every time we indicate that carbon 14 decays to nitrogen 14. So we do a shortened sentence that looks like this. I'm going to write carbon 14 as an isotope, and it's going to decay. Decay means it's going to change into something else. So I'm going to write an arrow that shows that it changes into something else. That something else is actually two something else's. It decays into a beta particle and a nitrogen 14 particle. I'm going to draw those. A beta particle, here's a beta, that's how the Greeks write their letter B, has zero mass because it's like an electron, and it has a -1 charge. It also, and because it's also, I'm going to write a little plus. So it's this plus that. It's a beta particle plus a nitrogen 14 particle. Okay? Nitrogen 14 has this symbol. Nitrogen has 7 protons, has a total mass of 14. This is a reaction equation. It's a nuclear reaction equation. And I want to point out some very specific things. On the left side, this is the parent isotope. Sometimes there are multiple parent isotopes. And on the right side, these are what we would call daughter isotopes. You start with the parent and you generate the daughter. One other thing to note, look at the amount of protons on the left. There are 6 of them. That is, before the event happens, the reaction happens, there were 6 protons in that carbon. Look at the right. Nitrogen had 7 protons, but the beta particle has -1 protons. 7 minus 1 is actually still 6. So the total charge, you can think of this as the nuclear charge on the bottom, has not changed technically from before and after. So what we have is conservation of charge. Whatever we have on the left is whatever we will have on the right, on the bottom. Well, look at the top. On the top, the carbon had 14 mass. That's 7 protons, 7 neutrons, but it had 14 total massive particles. After the event, the beta particle has 0 mass. The nitrogen has 14 mass. 14, and then 0 plus 14 is still 14. So it's also true that between the left and right sides of this equation, we must conserve mass. So we have conservation. Mass. That's a sample nuclear reaction. Now this, I guess technically would be considered a fission event because we started with one object or particle and it generated multiple particles. It fell apart into pieces. If we were going to do a fusion event, let's try a fusion event. So a fusion event would be something like a deuterium molecule. Okay, so you can have hydrogen, we call it heavy hydrogen, that has one proton and one neutron. And let's suppose that it slams into another heavy hydrogen of one proton and one neutron, excuse me. Those things can fuse together. And what they form is a helium nucleus with 2 protons and 2 neutrons. So let's examine that fusion event. On the left, we had 1 proton from this hydrogen and 1 from this hydrogen, and now we have 2 on the right. So that's conserved. The amount of nuclear charge, positive 2, has been conserved. On the top, there were 2 mass here and 2 mass here, and together that would be 4 mass, and yes, on the right, that has happened. Okay, so this is another example of a different kind of reaction, a fusion reaction as opposed to a fission reaction, but one in which we both conserve charge and we conserve mass. Now you can speculate. So let's do this. Let's do uranium 238 92. Suppose that I think that this element is going to react. It's going to undergo a fission event. It's going to fall apart. And I think uranium-38 does. And suppose that when it falls apart, it does so by emitting an alpha particle. Now, an alpha particle has 2 mass, right? It's like a helium nucleus that has 2 mass, and it has 4 total. Oh, sorry, it has 2 charge and 4 total mass. It's 2 protons, 2 neutrons. Well, if that's true, it would also leave behind some other daughter isotope, right? Uranium-238 and 92 mass would have to give away more than just 2 protons and 2 neutrons. There would be something left. Okay? We can predict what that will be. Let me show you. We started with 92 protons. 2 of them got ejected, right? Well, what's left? Well, there must be 90 more protons somewhere. So whatever we ejected has 90 protons, is the other daughter isotope. 238 was the total mass. We lost 4 of that total mass. So what's left? Well, there would have to be left. 238 minus 4 would be 234. What element would that be? Well, we will have to check our periodic table. The thing that tells us what we are is our number of protons. So let's look. I'm looking for number 90. And I look right there, and I see thorium is number 90. So this is an element that I would have created. I would have created thorium. Okay? This is how to balance what we would say a nuclear reaction. If you know the other pieces, you just have to make sure that the charge is conserved and the mass is conserved, and you can use the number of protons to determine the element. So back in the day, I say the day, probably the 1800s, everybody was interested in this chemical right here, gold, number 79. Gold was super expensive and hard to find. And part of the reason gold is hard to find is that in that fission reaction, remember I talked about, in that fusion reaction that I talked about, anytime you try to make something heavier than iron in a star, you lose heat. So it's hard to get all the way to gold in a star before the star goes dead. There's just too many more elements in the way to build up. So much fusion, you would use up all the material, the star would lose its energy. But certain stars, when they die, they compress inward and they explode outward. It's called supernova. And that compression can actually cause a whole bunch of little fusion events on its way out. So if it dies by exploding, that's where you can sometimes get some gold. So the fact that we have gold here on Earth at all is probably because way back in the past, some star went supernova and exploded. Anyway, these original chemists, they were called alchemists, were like, hey, we can use chemistry to make some gold. And they were never ever very successful. Well, I just showed you that we could take uranium. If it got rid of an alpha particle, it could turn it to thorium. So with a nuclear reactor, you can actually get fission events all the way down from some heavy element to gold. In fact, what they were trying to do, these chemists were trying to turn lead into gold because they were similar masses. Lead is very cheap, gold is very expensive. Okay, well, we can do this nowadays. In a nuclear reactor, we can bombard lead atoms with radiation until they become unstable, and then they fall apart and they turn into gold. It's been done. The problem with this is that most of the nuclear reactors use materials that are way more expensive than gold. Like some of these uranium plutonium isotopes are far more expensive than gold is. And so we wind up spending more money than the gold is worth to create it. The other problem is the gold that we create tends to be radioactive gold. It tends to be emit its own types of dangerous radiation, which is not safe. So if you were to like make jewelry out of this gold, you would get very sick. But that's how it is. It has been done. It has been proved. All right, that is our lesson on balancing nuclear reactions.